Yeast is a single-celled microorganism that occurs naturally in the wild and has slowly been domesticated for the production of various foods and beverages, such as bread, beer, and wine. In winemaking, yeast are exposed to challenging conditions, including low pH, high sugar, and in turn high ethanol environments. Therefore, strains need to be selected with this in mind to ensure the completion of alcoholic fermentation. Alcoholic fermentation involves the conversion of sugar to ethanol and carbon dioxide. Ethanol production is considered an evolutionary advantage in order to compete with other organisms for resources while also producing ethanol, a toxic substance to most other organisms, including themselves. As ethanol concentration increases, the integrity of the yeast cell is compromised. Ethanol toxicity impacts the plasma membrane, resulting in increased fluidity, which allows protons to move through the membrane, resulting in intracellular acidification. This ultimately impacts the growth of the cell and thus the viability. Other implications of ethanol stress may include denaturing of proteins and inhibition of glycolysis and amino acid transport pathways. If this occurs, the fermentation will become sluggish or ultimately stuck. With a changing climate involving warmer temperatures, sugar accumulation in grape berries are expected to increase, resulting in higher ethanol concentration wines. Therefore, research into the genes that might enable a higher ethanol tolerance is an area which would benefit wine quality in consideration of the likely future challenge to the industry, especially in warmer regions. Research conducted by the Wine Research Center at the University of British Columbia in Vancouver focused on two strains of Saccharomyces cerevisiae, S882C and M2, in order to determine which genes are linked to better tolerance of high ethanol conditions. The genes found to be associated are RCN1 and RSA3. These genes are located on chromosomes 11 and 12 respectively. When these genes are present, the resulting phenotypes observed include resistance to cell wall degradation and higher osmotic pressures at higher alcohol concentrations and higher tolerance to heat and oxidative stress. These are all typical environmental conditions associated with advanced fermentation. More specifically, the gene RCN1 regulates calcineurin during calcium signaling, which is stimulated in a stress response, enabling cell wall integrity and repair. This signaling activates transcription factor CRZLP, which induces transcription of RCN1. This enables higher copy numbers so that the yeast is able to adapt and continue to propagate in these conditions. To aid this, RSA3 acts as a growth enabler in these environmental stresses. Understanding the way organisms interact with their environment on a genetic level is very valuable. On top of being able to make phenotypic observations and selections, a genetic understanding enables the comprehension of an area as well as the possible manipulation to further refine this. This is relevant to yeast selection in the modern wine industry. In a time where the industry is refining the production of wine, both in efficiency and quality, the understanding and selection of effective, suitable yeast is vital, especially in the context of climate change, where higher ethanol concentrations are to be expected. With a genetic understanding of key functions of effective yeast fermentations, as well as the technology to manipulate these, there is the possibility that yeast strains may be further refined to suit future conditions and help shape a better product. One way of doing this is through genetic modification of yeast. This allows us to manipulate and develop these favorable or selected characteristics and is an effective way to apply the knowledge and technology currently available. Currently in Australia, the use of genetically modified yeast strains is not permissible. However, it will be interesting to see where this discussion goes in the future and what possibilities could be enabled if this changes.